Okay, so in the last class we have been discussing the random walk, one dimensional random walk, but now the objective was to look at the probability distribution of the end to end distance, and so far what we have been able to is derive this particular relation for the probability of having certain end to end distance R e for a walk of m steps of the drunkard as something of this sort, where we have already made use of the Taylor series expansion, we assumed that m is very high. So now what we will do is we will use the what is known as the Stirling approximation for the factorial when the value of m is very high. Okay, this really works only at high value of m, and the reason why we have been doing this again is because the factorials of like large numbers are difficult to evaluate. That's one reason, and the other reason is we want to go towards the continuum limit when m is very high. So if we do this, this particular approximation is given like this. So I can approximate, and you can try to see how it works for large values of m. So it really works well for m higher than 20 or 50 and so on. Particularly our polymers are really larger values of m. So if I take a ln of m star m factorial, what do we get from this relation is ln of square root of 2 pi m plus m ln of m minus m. Okay. And so if I put this particular expression in the earlier result that we have derived, what we will have is something like this. And if I further simplify, I can write this particular term as something like this. So there are certain cancellations here. This will cancel with that, and this will cancel with that, and this will cancel with that, and what do we have is which in turn give rise to the relation and which happens to be in the form of what is known as a Gaussian distribution. So, now we can see from here, when the RE value is very large, then the probability to find that RE will be smaller, because the RE appears in the exponential with the negative sign. And so, the configurations will have which are like more stretched or having a higher value of RE will be less probable. Okay. The smaller values of RE for the same reason will be more probable. What they essentially mean is a folded configuration of a polymer is more probable compared to an stretched configuration. Okay. And if I plot this particular relation against RE, what we do get is the distribution that is the Gaussian or normal distribution. Where my PREM again is okay. So, we can compare this with the standard form of the Gaussian distribution, and we realize that the prefactor in the standard form is slightly different. Okay, so, let us look at that. So, the general form of Gaussian distribution is given as, for a random variable x, that is sum of random variables xi for I going from 1 to m, we can write p x m, that is now the probability density. This was the probability and this is the probability density, and this is given by 1 by under root 2 pi m sigma square exponential of minus so keep in mind that this is the average of xi values. Okay. So, if I compare this expression that is present for the general form of Gaussian distribution with what we have derived, then we can associate the RE as the sum of the bond vectors BI. In any case, it is like one dimensional. So, we have assumed that B equal to 1. So, it can be plus 1 or minus 1. So, in that case, the average of BI in our case is 0, because the drunkard can move both left or to the right with equal probability. And so, I can associate this with my x, this becomes x bar, and this becomes my capital X. Sigma in this case is 1 if I compare the two expressions, and then what do I get is basically the same expression that we have derived earlier, except for the fact that there is a factor of 2 that is additional in the equation we have derived. So, this will give you and the reason why this happened is not because we derived it wrongly. The reason why this happened is we have to normalize the probability density, just like for a discrete distribution, the sum of the probabilities of all the possible events must be equal to 1. Similarly, in the case of a probability density, what we should have is, if I integrate the probability for all possible values of Re, we must get it equal to 1. Okay. And therefore, we can correct our probability function just by multiplying or dividing by a factor of 2 that appears because of this particular normalization. In any case, the factor does not contain the Re. What is essential to us is the fact that the probability density in our case is proportional to the exponential of minus Re square by 2m. Okay. So, although we have taken b equal to 1 here, if we started with say b as a finite value b, then in that case we will have a b square appearing in this equation. Okay. This is the way we can typically proceed, keeping in mind that whatever the probability we derive from a discrete distribution has to be normalized again for the continuous distribution. And essentially what we are able to show is, if I look at the random walk problem, in that case what we actually got is known as the binomial distribution, and the same thing that you get if you think of the coin toss problem. And for large values of m, or the number of samples, the binomial distribution approaches the Gaussian distribution. This is one of the tenets of statistical mechanics. Then when the number of samples become large, in that case all the distributions that we get in the discrete space approximates to the Gaussian distribution in the continuous space. Okay. This is not really true only for the binomial distribution, this is true for other kinds of distributions as well. So, this is related to what we know in statistical mechanics as the law of large numbers and what we know as the central limit theorem. Okay. So, the graph again looks like what we have here, except that we have to normalize it. So, we have to divide it by a factor of 2. Okay. So, in fact, it turns out that although we started from this particular Stirling approximation, we could have started with a simpler Stirling approximation, assuming that the first term is smaller compared to the other. So, in many texts you will find the Stirling approximation written something like this. And we can see, like, we can again put the same expression in the equation we had from the last class, and see that we will go back to the same equation that we have derived. So, let us try that. So, what we had was ln of m factorial ln of p r e m is equal to ln of m factorial minus 2 multiplied with ln of m by 2 factorial minus of m ln 2 minus of r e square by 2 m. And if I now approximate ln of m factorial as m ln m minus m, what we do get is this quantity here is equal to m ln m minus 2 multiplied by m by 2 ln m by 2 minus m by 2 minus m ln 2 minus r e square by 2m. This thing we can write again as m ln m minus m ln 2 minus m, and again we have similar cancellations. And we get this as minus r e square by 2m. We do not have the other term that we had earlier, so we do get so compare that to what we have derived earlier. So earlier we had a factor of under root 2 by pi m that is not appearing in this equation because we ignored a term in the Stirling approximation. Nevertheless, when I apply the normalization, I will get the same factor appearing in the equation, and that will give me so all we care about is the term that comes inside the exponential. The prefactor is simply coming by the normalization. Okay. So now let us think of like what would happen if I think of a 3-dimensional random walk. So you can decompose the 3-dimensional random walk as a random walk in x direction, random walk in y direction, and random walk in z direction. And why I am saying this is because let us say if I am doing a random walk in 2 dimensions, then this amounts to a random walk in x and a random walk in y, and the same idea we can extend to random walk in z. In other words, my end-to-end distance vector can be written in terms of its components where this and this, these three are the components in x, y and z directions, and Ex, Ey, Ez are the unit vectors in x, y and z. Okay. So if I think of that 3-dimensional random walk for Re, I can think of it as a product of 3 random walks in each of the 3 directions. And now we can write the equation that we have derived earlier . So I am putting a b square back here. B was assumed to be 1 in the derivation. So I can write this equation as something of this sort. So now this was for a walk only in 1 dimension, but now since we look at the 3 walks in x, y and z, what I will essentially have is P of 3D will be Now, we can note here that even for the 3-dimensional random walk, we have derived R e square is equal to m of b square. So, now I can write the R e square in terms of the components and there is no reason why these 3 terms will be any different, because if I look at it, the walks in the 3 directions are almost identical. So, there is no particular preference to any particular direction. So, what I can say now is so if I put this expression in what we have been deriving, what I end up getting is 3 by 2 pi m b square to the power 3 by 2 exponential of minus 3 by 2 r e x square plus r e y square plus r e z square, which in turn is again equal to r e square, and this has to be divided by m b square. Okay. So, what I have is something of this sort. Okay, so we have got this particular equation. Again, it is a Gaussian. The prefactors have changed, and now it is normalized again because we have started from the continuous distribution. So, we do not need to normalize again. So, what this amounts to is I can now write my probability distribution or probability density for a 3-dimensional random walk again as a Gaussian function, but now along a vector, but in reality this is a plot with 3 axes, that is REX, REY or REZ. The other way to think about it is this particular distribution is identical to the product of the 3 distributions that we get along the x, y and the z axis. Okay. That is one thing to gain from this discussion. The other thing is, and that is what now we will allude to, is we can associate this probability distributions in terms of the elastic energy of the chain, and this happens because we know from again from thermodynamics that the probability to get a state of a system with an energy E is proportional to exponential of minus E by kBt. What it means is, as the energy of the states become larger, the probability to find them become smaller. Okay, we can think of this in many ways. So, if I think of, for example, an electron, the ground state will have the least energy and that's most probable. The excited states will have lower energy and they become progressively higher energy and they become progressively less probable. Okay, so if I compare this with what we have obtained, so what we have is our E by kBt is equivalent to what we have derived earlier, the 3 by 2 Re square by Mb square. And so I can associate an energy E with my polymer chain having an end-to-end distance Re as something like this. And what essentially it means is, if we have say two conformations of polymer chain, this one and that one, and if this configuration has an Re which is lower than the other configuration, then then in this case this will have more probability than this particular case. Okay. In other words, this configuration has lower energy than that configuration. So, we can start thinking of the analogy with a spring. So, if the spring is more stretched, it contains more energy. If the spring is like less stretched, it contains lesser energy. So, in this case, this extension of the spring is represented by my end-to-end distance, and I can think of a spring constant and going to the idea of the spring having the energy half of k x square. We can see from here that my k is equal to 3 kBt by mb square, which becomes my spring constant. Okay. So, in this way I can represent different conformations of polymer chain as having a length Re of the spring, and if the k is changing, that give rise to a stiffer spring or a flexible spring. The higher values of k will correspond to more stiff spring. Okay. And now we can see like how is it happening, because if m is larger in my case, my k becomes smaller. Okay. So, as we have a longer polymer chain, it will have more flexibility because the value of the spring constant is lesser. In other words, since the elastic energy is half kx square, it will cause lesser energy penalty if I try to stretch the spring than compared to the case when k was higher, which will happen for the case when m is lesser. So, in this way we can say that the elastic energy of the polymer chain, so I will associate this E with an elastic energy, has entropic origin, and we will see like how this particular result become very important in the next class. So, thank you.